so we're going to finish up talking about bonded compounds and forces in bonding forces, basically. We're talking about intermolecular forces. So we've talked about the forces that are between the actual atoms in a molecule. Those are intramolecular forces. Now we're going to talk about the forces between two molecules in a molecular substance. So like two molecules of methane or propane or sugar or phenylsalicylate or citric acid, where you have a molecule sitting next to another molecule in that compound. And we kind of talked about this already. You know that molecular compounds tend to have low melting points because the forces between the molecules aren't nearly as strong as the forces within an ionic compound in that whole chunk. So generally they're weaker than the bonds in an ionic compound, and definitely weaker than the bonds in the atoms between a metal. And again, if we think about that whole melting point being a proxy for internal bond strength, you can melt sugar with a flame. You can burn sugar on the stovetop. You're not going to melt metal on the stovetop. If you want to smelt metal, you're going to have to build yourself a little charcoal burner in the backyard. You're not going to melt salt even in your charcoal burner in the backyard. So salt actually has a higher melting point than a lot of metals. It's easier to smelt gold in the backyard than it is to melt salt. So that melting point, boiling point stands as a proxy for the forces inside a substance. And intermolecular forces tend to be relatively weak. So one of the exceptions that increases intermolecular forces is polarity. What kind of molecules have poles? Polar molecules. It's like who's buried in Grant's tomb? Sherman? No. So polar molecules have poles. And those, what we talk about is dipoles, which are, di means two, something that has two distinctly opposite poles, that negative and positive area of partial charge on a molecule. So they're created by opposite charges separated by only a short distance. And what happens is within a substance, you get dipole-dipole forces. So all the little positive ends of molecules are attracted to all the little negative ends of the other molecules. And so they kind of tend to line up in one way. So polar substances tend to have higher, what? Melting points and boiling points than we would otherwise expect. So we can look at a molecular compound and say, well, that's weird. For a molecular compound, it's got a relatively high melting point. We would tend to think, I bet it's polar. So things that are polar tend to have, you see these sort of what look like inflated melting and boiling points because those dipole-dipole forces are holding things together more tightly. Now, they don't operate, within an ionic compound, those forces of attraction run in a lot of directions. Within a metallic compound, those forces of attraction run, they're far-reaching. With dipoles, it's only momentary. I was thinking of dipole moments. It's only between, this molecule and this molecule. I should make those M's, shouldn't I? Molecule A, molecule B. It's only between these. It doesn't work all the way over here. So they're short range, these dipole forces. They're localized. And then we have hydrogen bonding. So hydrogen bonding, as you would guess, involves hydrogen. Duh. And when we have hydrogen bonded to something very electronegative, hydrogen is not very electronegative. So the other thing tends to pull a lot of the electrons off of the hydrogen. So hydrogen very often, and if we think about water, hydrogen ends up sort of sticking out with let me do a better job drawing that, sticking out as mostly a proton with most of the electron cloud being kind of sucked down into the rest of the molecule. What that means is that things that have little hydrogens sticking off them, and we said, with Mickey Mouse, little positive ears, those hydrogens are mostly little nuclei. And those little positive nuclei have these attractions, especially to if there are unshared pairs on other nearby molecules. Well, of course, in the case of water, you do have those unshared pairs there, which give, aside from the fact that oxygen's pretty electronegative and it pulls a lot of the electron cloud that way, you have those unshared pairs there, so you get forces of attraction between the hydrogens on one water molecule and the unshared pairs on the other. So they tend to line up, and that's actually a lot of why, we have surface tension in water, because there's a sort of skin formed on the surface, so you can float a needle on the surface of water if you're really careful. Forces of adhesion and cohesion in water, where water is attracted. Remember, water is only attracted to two things in the entire universe: itself and everything else. So that's because largely of those hydrogen bonds. Water tends to cling together, but it also tends to be attracted to other surfaces. And hydrogen bonding, again, just like dipoles, it increases the boiling point, and it creates surface tension. Water striders, the little bugs that you see skating on the pond or on the creek, they are walking on surface tension. They're basically walking on a skin formed of water molecules that are tightly held, both by just dipole forces and by hydrogen bonds, where there's sort of a skin formed on the surface of the water. So we also have what are called London dispersion forces. I don't, and I've never really dug deep into it. I don't know why they're called dispersion forces when they're actually a force of attraction. To disperse means to break up, to send away. They are weak intermolecular forces between nonpolar molecules, and these actually do happen in noble gases. Wait, noble gases don't have any forces of attraction. They're completely above that. You get moments. So what are electrons doing at any given moment? Moving, not orbiting, be careful, zinging around like little gnats in a cloud. We don't want to think about the racetrack, because it's a useful model, but for this, we want to think about little gnats moving in a cloud. So what can happen sometimes is we get what's called a dipole moment. We basically get a little instantaneous dipole. So if I have a little positive nucleus here, and it's surrounded, let's say, by, we'll make these little sp, oh, these are terrible. These are just terrible. I was trying to make these sp3 orbitals. So there's one sticking off in that direction. These look like, it's awful. Tell you what, we'll just do a linear. How's that? I think I can manage a linear. So let's say we've got two bonding orbitals sticking off in opposite directions. And of course, they each have those little electrons buzzing around in them. Okay? Moving randomly, moving rapidly, zing, 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 zing. You can't keep track of them. It can happen that you get a moment where all of the electrons in a given atom are on one side of the atom. Just randomly. It can occur. Does it? Oh, not a particle physicist. I'm told, however, that it can happen. And when that happens, suddenly what you have is a region of negative charge here and a region of positive charge there. When that occurs, you have this little tiny second, millisecond, millionth of a second probably, where you have a dipole. And then it's gone. It's over, because they keep moving. So we call these London dispersion forces. They're the least important of the intermolecular forces that you should know about. But if you're going on in chemistry, depending on what kind of chemistry you're doing, it could be important to you. That is it for Chapter 6. That's all you're going to do with chemical bonding. So, homework. due Monday. I'm going to add probably 2 problems on the intermolecular forces. Monday we grade, then you start doing your crystal solutions. Tuesday you have your test, and then you'll continue crystal work. And I'll have sort of a preview for Chapter 7, and that's what we got.